minus H. Okay, for our group, we represent about the Lagrange multiplier. Okay, for my part, I represent about the history. First of all, we will come out the history of the creator of the Lagrange multiplier, which is Joseph Louis Lagrange. Okay, he was born at Turin, Italy on 25 January 1736. Okay, then we will take a look on his achievement. Okay, on 1776, he is director of the Berlin Academy. Then he wins several prizes of French Academy of Science. 1787, he became a member of French of Science. He also involved in decimalization in revolutionary France. He is the first professor of analysis of Ecole Polytechnique. He also founding member of Bureau des Longitudes. On 1799, he became a senator. So basically, from here to here, this is his achievement, as he is the greatest mathematician on 18th century. Okay, before he come out the Lagrange multiplier, he is the creator of variation, derived Euler-Lagrange equation for extremum functional. Then he also extend a method of deriving of Lagrange multiplier. Okay, next we will discuss about the history of the Lagrange multiplier itself. Okay, it is used in calculus to find maxima and minima of functions subject to constraint. Basically, it takes about more than 20 years for the Josephus to come up with the idea of the Lagrange multiplier. Okay, for his first concept is the Lagrange 1764. He presents his new conception in Memoire, written to answer a question advanced in 1762 by the Academy of Paris. He is concerning about the liberating of the moon. Okay, next is the Lagrange 1780. More than 15 years later, he outlined a more elaborate and general version of the same program. Okay, the program is the program of mechanic and analytic, Lagrange 1788. Okay, he came up with two ideas. First idea is the Vennerin principle, then the Alembert's principle. Okay, finally, he determined the general equation of equilibrium for problems with constraint, which is the Lagrange multiplier. Okay, this one.
Next, I will explain on how to prove the Lagrange multiplier. In Lagrange multiplier, we have two functions. The first function is the revenue function that we need to maximize, and the second function is the constraint function, and it is equal to a constant. For example, it is b. The value that we need to maximize is m star, for example. Okay. And from this graph, you can see that the gradient of the function f and gradient of function f is parallel. From this relationship, the gradient of f is directly proportional to the lambda and multiply with the gradient of g. Lagrange multiplier also proposed this equation, that is Lxy lambda is equal to fxy minus lambda gxy minus b, the constant, and the gradient of L is equal to 0 at the maximum point. To differentiate the Lagrange function to respect to x, respect to y, and respect to lambda. When we differentiate the L respect to x, it is equal to 0. Respect to y, it is equal to 0. And also when we differentiate respect to lambda, it is equal to 0. The differential of function f respect to lambda is equal to 0, definitely, because there is no lambda here. Okay, for the gradient of L to be equal to 0, we have to maximize the value of x, y, and lambda. These values, we put a star to mark that it is the maximum value. M star is equal to fxy from there. And for us to include the b, the constraint function, to be in the first function, he proposed this equation, that is lambda star is equal to dm star over to db. Okay, and the new equation from this equation is L star x star y star lambda star is equal to fxy star minus 2 lambda gx star y star minus b. From this equation, we can see that gxy minus 4 is equal to 0. So we can cancel out this. Okay, from this. when we differentiate dl respect to b, there is no b here, we can cancel out this equal to 0. So this, when we differentiate respect to lambda, it is equal to lambda. But to involve b as a constant, b is the constant of the constraint function, we differentiate again this one, dl over db. Differentiate L respect to x star. This one is equal to, from this it is equal to 0. From this one it is equal to 0. And from this one it is equal to 0. And it is equal to 1. So we get back dl over db is equal to dl star over db. And from this L is equal to m star because this value is equal to 0. So we can prove that the lambda star in terms of b is equal to this one is proved. That's all.
Hi, my name is Nurushan Husna binti Muhammad Saimi, and I'll present the derivation of language multiplier. Okay, language multiplier is to maximize the f function on the surface of x. Here is the surface of S, and we got three function lies on the surface, which is P, Q, and R. Okay, here P and Q is not perpendicular to the surface, so the dot product of P and Q to the surface will not come out 0. So we cannot determine the P and Q is a local maximum or local minimum. But for the R is perpendicular to the surface. So when the gradient of R to the surface will produce the 0. Okay, next is the S. The S, the G, the surface itself will produce the normal, which is G here and here and here. So G, the gradient G and the surface will produce the 0. The dot product of G and the surface is 0. So we can see here G and R is parallel. So when it is parallel, we can conclude that R is lambda G. The gradient of R is lambda G. Here we can prove that this is the derivation of language multiplier.
Hi, my name is Marsha binti Muhammad Najib, and I'll do the parts of applications of Lagrange multiplier. Well, basically, the Lagrange multiplier methods are widely used in solving extreme value problem, including in sciences field, engineering fields, and also academic fields. Well, have you ever wondered how the forecast actually works, where they find the maximum temperature in that certain area and also the lower temperature in certain area? Well, basically, it is applications of the Lagrange multiplier itself, where this is the functions, C is the constraint. Okay, basically, this is the functions given, f1, f2, f3. x1, x2, x3 is basically the output power by the generator 1, 2, and 3. This is the functions that are needed to be minimized. Okay, the objective is to minimize the cost per hour. So what we have to do is, we set up the functions, which is f1, f2, and f3. We plug in all the value over here. And then the constraint that are given is x1, x2, x3, and minus 952. Why? Because x1, x2, x3 is the output power of the generator. So this is the maximum things that can be done. And then this power is needed to overcome 950, which is the load over here, joule per second, megawatt. Okay, and then by applying the Lagrange multiplier, we can see that the gradient f is equal to 0, right? So what we have to do is just plug all the value over here, x1, x2, x3, just plug in over here, x1, x2, x3, and x4, which can be found. I mean, if you plug in all the value, you'll have -1, -1, -1, and end up with 952. So by this equation, when you solve this equation, you have to find the x1, x2, x3, and x4, which is x1, x2, x3, x4. So you will have the value of x1, which is 112 megawatt, x2 560 megawatt, X3 280 megawatt, where when you solve this problem, you'll find out the lambda is basically $15 per megawatt per hour. Okay, back to our applications over here. As we have the lambda, we have the value of lambda over here. We can see that if you plug in all the lambda and all the value of x1, x2 and x3 over here, we can see that the cost, is the F, is equal to 7616 per hour, which means these are the costs. These are the costs, hourly cost production. So by implementing the Lagrange multiplier over here, we can see that we can minimize the function. We can minimize the hourly cost of productions for any companies.
So now we are going to use Lagrange multiplier to solve an example. So we are going to, there's a production which is modeled by a function f(xy) equals to 100xy with a constraint whereby x represents the units of labor and y represents the units of capital. Each labor unit costs 200 and each capital unit costs 250. The total expense for the labor and the capital cannot exceed 50,000. So this is our function, this is our constraint. So first we have to form the equation as given by Lagrange multiplier's formula, where the gradient vector of xy is equals to a parameter lambda times the gradient vector of the constraint g. The partial derivatives of x, y and lambda, we can solve for lambda in terms of x in terms of lambda, and y in terms of lambda. So y will be equals to 2 lambda and x will be equals to 2.5 lambda. So we take this and we substitute the value of x and y in terms of lambda into the constraint, the partial of lambda. So minus 200 times 2.5 lambda minus 250 times 2 lambda for y plus 50,000 is equals to 0. So we can solve for lambda from here. So lambda will be equals to 50, and we take this lambda value and substitute into equation 1 and equation 2 to get the value of x and y. So from here we can get 100 y is equals to 200 lambda, and lambda is 50, so 100 y equals to 200 times 50. So y would be 100, and then we solve for x by substituting lambda equals to 50. So 100x equals to 250 times 50. X would be equals to 125. After getting the value of x and y, we substitute it into the initial function to find the maximum production with the given constraint. So the function is f xy equals to 100 xy, which is equals to 100 times x, which is 125, times y, which is 100, and then we'll get the maximum production, which is which is 1,250,000.